So first, I would like to thank the organizer to invite me to give this talk. And it's a great opportunity to share results with the community. I would like also to acknowledge my collaborator, Liz Huismas, and to Total Energies for funding the project. Today, I'm going to talk about numerical modeling of magmatism at rifted margins. So first, I will give a brief introduction. We know that rifted margins are formed as a consequence of continental rifting and breakup. And there are a lot of variations of magmatism along rifted margins. For example, some margins are volcanic with normal thickness of oceanic crust, like the Lofoten margin. And some are also volcanic, but with thicker than usual oceanic crust, like the Foley margin. And some are non-volcanic with extreme serpentinized mantle before oceanic crust. Today, I'm going to focus on volcanic margins. So here is a map showing distribution of different type of margins. The red lines show volcanic margins, for example, here in the North Atlantic, Central Atlantic, and the South Atlantic. We know that magmatism is a consequence of mantle decompression melting, which is dominantly controlled by mantle temperature. At a reference temperature, it will generate a normal 6 kilometer oceanic crust, and with high temperature, more melt is created. So high temperature mantle plume is the most commonly accepted model for volcanic margin formation. And successful examples include the Iceland plume and the Tristan-Cunha plume. However, it is not always easy to demonstrate the existence of a mantle plume, and many studies have been done before to resolve this difficulty. And most of the previous studies have been focused on a sublithospheric mantle. Here we explore the effect of the lithosphere. We know that the extension of the lithosphere may form different rift styles. It can form narrow margins where the crust sinks abruptly and with extrumed mantle, or it can also form wide margins with huge wide regions of thin continental crust and the earlier breakup of the mantle. And extension in these margins is highly depth dependent. So what are the consequences of different rift styles for magmatism? We use thermomechanical models to study this problem. Here is our model setup. It has horizontal layers of crust, mantle lithosphere, and sublithospheric mantle. An extension is applied in the lithosphere. The initial temperature is laterally homogeneous, and it has a constant potential temperature for the sublithospheric mantle. We apply two end-member crust rheologies, a strong crust and a weak crust, which are responsible for a narrow margin and a wide margin. The model includes mantle decompression melting, so we can predict how much melt is created. So here in the bottom, it shows a typical snapshot of our model result. The black lines show isotherms, and the red triangle is a melt window where melting is happening. On top is predicted melt thickness for different potential temperatures. And we see that at high temperature, thicker oceanic crust is produced. Shows reference normal global oceanic crust thickness, which we can use to calibrate our model parameters. And which it shows that 1300 degree is a good number for a reference mantle temperature. Next, I will show a model result. First is a reference model, which has a strong crust and a normal mantle temperature. On top is an animation. In the bottom is a snapshot. A red is predicted melt thickness. Now I will play the animation, and we see that deformation in this model is strongly localized in the center. So this model forms a narrow margin with sharp transition to a normal thickness of oceanic crust. Next, we look at model 2, which has a weak crust and a normal mantle potential temperature. We play the movie now, and we see that the deformation is decoupled in the lithosphere, and the mantle breaks earlier than the crust, which is a feature of depth-dependent extension. So with ongoing extension, melt is already created during lifting before crust breakup. So in the bottom, from the snapshot, we can see that the margin is very wide in this model, and the igneous crust is very thick at the distal margin. While after breakup, the thickness becomes a normal oceanic crust thickness. So note that in this model, we didn't introduce any high temperature anomaly, and the enhanced magmatism is a consequence of depth-dependent extension. Next, we change crust strength systematically from very strong to very weak, and we observe that margin weight becomes wider, and magmatism also increase. Then we measure the margin weight and melt volume in these models. So the margin weight is measured from the beginning of crust thinning to the last piece of continental crust, and the melt volume includes all the melt from the beginning until break up, and continue a little bit because the melt thickness does not immediately recover to stable thickness. And on the right side, it's measured data. The x-axis is margin weight, and here is melt volume. And we see that melt volume is linearly correlated with margin weight. At high temperatures, this correlation is still valid, except that both the volume and the slope is larger at higher temperature than the reference case. We established a very simple scaling law to predict the volume of melt as a function of margin weight and oceanic crust thickness, where oceanic crust thickness is a function of potential temperature. And on the right side, we compare, put them together, where the dashed lines is the scaling law with the oceanic crust thickness indicated, and the data points show a measured melt volume and margin weight from models with different potential temperatures. And we also know that global oceanic crust have a normal range of oceanic crust thickness between 4 and 8 kilometers, which indicate a normal temperature. So we can use this information to divide the volume and margin weight parameter space into 3 regimes. The domain between HOZ 4 and 8 kilometers is defined as normal temperature, and above is high temperature, below is low temperature. Next, we look at published cross sections that are constrained by both reflection and refraction data. We measure margin weight from the start of crust thinning to the last piece of continental crust. Melt volume measurement includes 3 components, the LCB layer, the SDR layer, and the intrusion in the crust. We have done our best to quantify the uncertainty in our data measurement. Finally, we have 14 conjugate margins with margin weight and melt volume listed in the table. Next, we compare model results with observational data. We have seen the background picture before. Now here, just to remind you that the gray data points are model results, and the dashed lines are scaling law with different oceanic crust thickness parameter. And we have defined the domain between 4 and 8 kilometers as a normal temperature domain, and above is the high temperature domain, below is low temperature domain. Now we project our measured observation data points on the plot and define the lowest points in the high temperature domain as excess magmatic margins, and in the normal temperature domain as normal magmatic margins, and in the low temperature domain as amagmatic. Now we look at the map on the right. We see that there is a cluster of excess magmatic margins near Iceland plume and at other locations in the Central Atlantic and South Atlantic. These excess magmatic margins require higher than usual mantle temperature. However, the excess temperature required is on the order of 50 to 80 degrees than reference, which is much lower than previously thought. Then we look at the green data points, which are the Lofoten and the Northeast Greenland margins and Colorado orange conjugate margins. These data points are classically known as volcanic margins. However, from here, we see that these margins, these are normal magmatic. They do not require high temperature anomalies. Finally, we look at the blue data points, which are, for example, the non-volcanic Iberia and the Newfoundland margins. We see that as expected, these data points are located in the low temperature domain. However, we do not interpret that these margins are simply formed by low temperature mantle, but suggest that there may be other mechanism to explain the absence of magmatism.
You're just past the 10-minute mark, please.
So an outcome of our study is that we have classified rifting margins into 3 modes instead of the classical 2 end members. And the classical volcanic margins now is split into normal magmatic margins and excess magmatic margins. In the classical view, volcanic margins is usually associated with high temperature anomaly, while in the new classification, those normal magmatic margins, they do not require high temperature anomaly. So to summarize, we have shown in numerical models that depth-dependent wide rifting may enhance magmatism, and the melt volume at volcanic margins is a function of margin weight and mantle potential temperature. And some volcanic margins may be generated with normal mantle temperature, and at some volcanic margins where high temperature is required, lower excess temperature is required than previously thought to explain the observed magmatism. That's all my talk. Thanks.
Thanks you, Ganglu. If anybody has any questions, as always, you can put it in the chat. I have a question about your numerical models. You have quite a bit of asymmetry in terms of the magma volume produced. What is dictating that asymmetry?
It's a good question. The asymmetry is controlled by the, how we do the predict the thickness of igneous crust is that we affect the predicted thickness at the surface velocity. So it's easier to see that it's controlled by where the final breakup in the. So I play this model. It is controlled by where the final breakup of the inner crust is, and it inserts or cut the initial peak. Then it becomes asymmetric.
Does it vary from run to run? Or is it very stable?
It's a good question. From models to models, the asymmetry changes. But we didn't repeat the same model from, so I would say that it changed when we have different rheology or temperature distribution.
Okay. Interesting. Any other questions? I know there's some numerical modelers in the crowd. There's a question from Robert Winch. Would you like to ask your question directly?
Okay, this is a question maybe for all 3 of our speakers. I'm interested in off-axis extension and off-axis volcanism. It seems that with a weak crust, we might get wide extension in the crust. And I wonder what controls the distribution of that extension off-axis and volcanisms that may intrude on off-axis extensional faults. Does that make any sense?
Yes, I'm not sure I exactly can answer your question. So that how this distribution is controlled. It's actually controlled in our model. The melt is assumed to be extracted vertically. So when there's a crust and the melt is happening here, then it goes to the up point. So it is controlled by it is controlled by the relative location of the continental crust on top and the melt system below.
Yes, but in that case, the model controls where the extension and volcanism will be. And I'm wondering whether the well-known extensional basins on the margins of North America in the Triassic, Jurassic times might be off axis. Everyone seems to think that it was on axis and somehow the axis moved. And I wondered if in fact it's off axis volcanism at about the Triassic, Jurassic boundary. Maybe other speakers have any ideas about that. Or maybe others in the audience.
Any takers? Our next week's, the speaker in 2 weeks' time might be able to address that perhaps. Any thoughts from the crowd? Or any other questions for Ganglu? There's a question from Phil Rezor. I think we might, Robert, I think we might have to leave that one on the uncertain. Oh, somebody's got their hand up. Zubo?
Hi. Hello.
Yeah.
Yeah.
Are you going to answer Robert's question?
Oh no. Oh, sorry. I have a question for Lou. Yeah. Not answer Robert's question. Yeah.
Okay, go ahead.
Hi, Lou. I have a question about your models. Yeah. Do you set the different rheology for the upper crust or lower crust or not? Yeah.
The rheology we use for the crust, it's the same. So we have the same crust for the up crust and the lower crust, and the same for the up crust, lower crust in all models. And,
okay.
And the parameter we use, it changes, is called the viscosity scaling factor. So if this factor is larger, it's stronger, and this factor is smaller, then it's weaker.
Oh yeah, I mean there's a paper. I mean, using the extension model to study the volcanic the continuum margin of the South China Sea. So the author used this weak middle crust to simulate the wide margin of the South China Sea. So I wondering, do you have do some comparison with the results with your results with the observation in the South China Sea?
So actually, I'm doing some models. It's a very interesting topic, and I'm doing some models, and I already have some preliminary result to compare with South China Sea. So yeah, what I can say is that it's an ongoing work.
Lights have gone out.
It's dark now. I don't know. Yeah.
I'm just looking, there's one question in the chat and then Ritska put his hand up after. So Phil Reeser, would you like to ask your question or would you like me to ask it for you? And we need to wrap up shortly because I realize we're at maximum time.
I think my question was actually just answered, that it's this viscosity scaling parameter. I guess I had a follow-up question, which is, what does that correspond to in a geologic system?
So one of the reason, one of the possibility in geological explanation is that there might be more water content. This can become make crust weaker, and another reason is that there might be the temperature will also change the rheology. However, we use same temperature in all models, and so any temperature effect are equivalently put into the crust rheology in our models. Yeah.
Thanks.
And the last comment can go to Ritska.
Yeah, I can just briefly comment on Robert's question of these offset basins. The basins, for instance, offshore, basically between Nova Scotia and mainland Canada, you have the same ones out of further south. They're typically should be considered basically mostly upper crustal extensional basins. They don't have any post-drift. And if there's no post-drift, then it indicates there's very little mantle thinning, right? So in that sense, you would call them off-axis. I'm not sure if that answers your question, but I think it's, at least that's what I would think about those. So yeah, I would consider them off-axis for sure.
Okay, perfect. Thank